46 times. They probably did their quick port and got a 5 times speed up, and were like, gee, that's pretty cool. All right, how can we get that faster? And they fiddled a little bit, and they probably got up to like 40 or 50 times speed up. And then they had to sit down and do a lot of really hard debugging and optimization work. But they could eventually get to this. The only way you get to that, though, practically speaking, is by really knowing the architecture, how the memory is used, what the cores are doing, and knowing that and planning for that in your algorithm and the way you use everything, you can get to that. And some of these numbers are with the help of people in NVIDIA. You know, we've got a dedicated set of teams that are developer relations, developer tech. They basically, you know, go out to universities, corporations, anybody doing this kind of work. If they say, hey, we need some help, these guys come in and look over what you're doing and help you out and get, you know, really get you optimized. Not all of these are using our teams. I don't know any given one of these if they had help from us or not. I would say mostly they probably didn't. And this is what they got. So anyway, I won't harp on that too much more, but this is why it's such a big deal, talking about general purpose. And these are just a couple instances of you know, companies that went to this. So I don't know if you guys heard about this. This was kind of making some press recently and got some chuckles. But you know, shampoo research. Who'd have thought? But you know, if you're a bean counter, look at this. I mean, that makes a difference. If you can get a data center for $7,000 that's going to do what your $128,000 system did, that's a no-brainer. I mean, it might be really hard to do, but you're going to tell your programmers, like, as long as I'm paying you less than $121,000 a year, that's a really good deal. As long as it takes you less than a year to do it. If it takes you 2 years, then forget it. But if you can do this in 3 months, basically port your stuff over to GPU, that's a really good investment. And then just on power, you know, well, 19 watts versus 19 kilowatts versus 1 kilowatt, yeah, cool, all right. 45 versus 1200, that starts to make a difference because you're actually starting to change the way the data center works. Instead of having to have a data center with a specialized air conditioning system just to keep your things from burning up and having your own power grid to keep your computers running, if you can essentially get rid of that, then you're saving a lot more than just the cost of the hardware and the computers. And new things can become available. I mean, some of these guys working on supercomputing systems are shelling out $100, $200 million for a ton. I don't know the numbers. I mean, you guys probably know better than I do. But you know, the size of some of these supercomputing centers running traditional CPUs and specialized communication fabrics and everything like that, these guys are starting to shift over to this now. And they're going to spend the same amount of money, but they're not going to be spending it all on air conditioning and power and these massive traditional systems. It's all going to be basically going into horsepower. So again, that's going to change what supercomputers can even do. Okay, I'm going to fly through these because it's not really the point, but I do want to emphasize that with the traditional graphics pipeline, you're kind of limited in what you can do. But now you can actually do radically different things by having general purpose computation. You can do the sorts of graphics algorithms that nobody would have even attempted to do on a GPU in the past. The one I really want to point out, well, so that's kind of cool, actually, but well, here we go. This is the one everyone cares about. Ray tracing is a very serial thing. The GPU is a very parallel thing. So how do you reconcile the two? I don't know if you guys know ray tracing super well, but the basic idea is you've got a camera with a lot of rays. You know, call it 1 million different rays that you've got to shoot out. And in practice, if you only shoot out 1 million rays, well, you're going to have some aliasing. So you really need to send out like 16 million rays. And then each one of those rays, if you want it to actually look good, when it hits the surface, it's going to bounce off. And if you want that to look good, you're going to bounce off like 16 other rays. And that's a really simplified version, but you're talking about, you know, several billion rays, maybe 1 trillion rays to get a single frame. Each ray is serial, but the whole thing is really parallel. So obviously, like, we want to find a way to use the GPU to do this. The traditional graphics pipeline is hopeless. The only thing in the traditional graphics pipeline that is going to help you is, you know, maybe some clipping, definitely rasterization, dedicated rasterization hardware, some other things like that, but it's a hard problem. But now that we have general purpose and we have so much independence between the different streaming, between the different SMs, this finally becomes reasonable. You can finally do this. You might not be able to do every effect today in a time-efficient manner. Like you might not be looking at perfect caustics right now. But this, you can do in real time. 30 frames a second, maybe 120 frames. I'm not up on what the latest ray tracing is, but everybody's looking at that. They might not say that this is the future of the industry, but everybody's looking at that. Intel, that was one of the things they're pushing with Larrabee. AMD, they're looking at that. We're definitely looking at that. So games look really good without this, but I have no doubt that when game programmers start using this, games will start looking a lot better. And eventually, the difference between games and movies, well, who knows? I don't want to make a lot of predictions there, but you can see where it's going. So using this general purpose computation hardware, mixing physics, CUDA, all of this with still doing graphics, you can do pretty cool things. Okay, so now actually kind of the history of GPU computing itself. So in the beginning, there was GPU. Like I said, 2003, people were trying to figure out how you could do solving large matrix equations and things like that just using the graphics pipeline. So you saw the graphics pipeline earlier. It's not clear to most people how you would do solve large matrix equations using that. You can do it, but basically what you have to do is you have to treat your texture as your data input and do all sorts of really weird multiple pass algorithms where you render a quad and each operation, each pixel in that quad winds up being one cell in your computation, and it might look at some neighbors, but you wind up having to do condensing passes and MIP maps where I don't know, it's painful. I did some of this and I wouldn't recommend it. It's kind of like finding out that you can go to the moon, but you have to climb a rope to get there. I won't break down exactly how GPU, how people shoehorn things in, but it was very tricky. And amazing, like some of the things people did with it, you wouldn't have believed was possible. You would read the papers and you would look at it and like, no, seriously? So it's definitely gotten more complex. Like cellular automata. All right, that makes a lot of sense. You could see how you could go from a texture to doing like Game of Life, or various things like that, with multiple passes on the GPU. PDE solvers, tricky, but you can kind of imagine. Ray tracing? No. I mean, people did it, but it was clunky. So this is just kind of talking about how people would actually lay out texture resources and use them with computation. I'm going to skip over that because it really is yesterday. So I mentioned Brook earlier. It was Stanford did a lot of really pioneering research and GPU work, and they were kind of the kickstart to making things much more generalized. And they were the ones who basically pioneered the idea of a stream, where you do some computation on a data and you stream that to your next kernel, and do more computation on it and stream it to the next kernel, and you're basically chaining kernels together and getting throughput. Each individual operation might be slow, but by chaining these streams of data together, you can get fast processing, or high throughput overall. And I won't spend a lot of time on that, but I will say one of the guys behind this, Ian Buck, is now the head of CUDA at NVIDIA. So he's been thinking about this for a very long time and is kind of pushing things. I think it was worked on internally in NVIDIA for a long time, but it kind of hit the public limelight in 2006. CUDA, it was the first way that basically let you do GPU